この配信はグラのスポンサーの提供でお送りします。Hello, hello everyone and welcome to another Friday night stream. I'm TheNando, a VTuber with a PhD in mechanical engineering, and today I'll be answering some more of your questions. Just going to yap for a little bit, making sure everyone has time to arrive, to make themselves comfortable and cozy. I do have 11 questions prepared. I closed the submissions because I don't want to go through an endless loop of more and more questions being submitted, but this will be the end of this series of questions. I will do more Q&A in the future, so if you had a burning question and couldn't have it addressed this time around, do not worry, there will be more. And let me say hello to our lovely viewers, the Nandos. I see Mi-chan on Twitch. Hello Mi-chan, hello Zazon, you were the first today, sniping that position away from Mi-chan. Stonks are in shambles. And of course, over on YouTube, Unfunny Failure, welcome, welcome. Glad to have you here today. And today, not today, lately, I don't know why, I've been feeling tired. Some people have asked that maybe I'm sick because tiredness is not my... I'm usually the kind of person who does a lot of things, but never feels tired for them. I mean, I have been working out a lot, but if the rumors are true, working out should give you energy. And my workout is a very peculiar one. It's a tired type of week. I do feel that. I feel like I feel tired, but I have a feeling this week everyone is tired. For a lot of different reasons, but I have a feeling of that as well. One of my favorite workouts right now, GeoWizard would be proud, is that I just pick a direction, any direction, and okay, I'm just going to walk in a straight line on that direction. And I've stumbled upon some wacky stuff already. It's cool. Doing exploration in real life, as long as it's safe. I do not suggest you do this without regards for your own safety, as long as it's safe and you can do it. Exploring and doing map quests in real life is really cool. Q&A part 2, yes, let's go. And it does make me happy as well to see, thanks to Van's gifted, to see more badges of subscription over on YouTube, over on Twitch. It does make me happy to see, because I like seeing the pocket watch. And of course, I'm waving back at you, Vexel. Welcome, welcome. Hope you're having a wonderful Friday. Remember that Randonautica app? Randonautica app. It isn't ringing a bell. Oh! Yes, I just googled it. Oh, yeah. And hello, Mutation. Welcome. I hope I'm pronouncing that correctly. I didn't know who gifted it to me, but huge thanks. Yeah, it was Van. Yeah, the Randonautica, that flew under my radar. And I mean, there was also like the huge craze when Pokemon Go first released, where everyone was walking and going to places thanks to Pokemon Go. Sadly, there were a lot of places that if you lived in the middle of nowhere, maybe that was my situation, where I was walking like 400 kilometers in 2 months, and people who were just spawning places were having more progress in the game than me, and I was like, why do you create a game like Pokemon Go and do not reward walking in it? I'm punished for walking. All I'm doing is hatching eggs by walking so many kilometers. Simpler times. Yeah, man, Pokemon Go, when did that release? It feels like it released ages ago. 2016. So 10 years ago. Damn. That is indeed quite a while. I remember when it was just Gen 1 Pokemons. Yeah, I had Google ready up. My apartment had a Poké Center within range and I was in bed. Yeah. 2018 is when it got popular. Oh, I played Pokemon Go before it was cool. I love cursive handwriting, by the way. I know that nowadays a lot of places do not teach cursive handwriting, but for me it's always been the best. It worked well when I was at uni, but it's not good where I live now. But yes, I have a PhD in mechanical engineering. I don't know how to write engineering. I hope I didn't do any typos. And I did a thesis in robotics. And I opened up a list for people to submit their questions. This is a Q&A. Let me just adjust the size of my eraser here. Okay, this should be fine. And today I'll be addressing more of those questions. Some of them were left unanswered from last stream. Others I have been submitted meanwhile. So let's head on to question number 1. Let's get into the flow. Once I get into the flow of engineering, my brain will start braining, as I said the other day, and things will start snowballing from there. So question number 1, we have Guts asking, was the first time you programmed during your thesis? What beginner mistake do you think you made at that stage? And at the time, was your mindset more, as long as it works, it's fine? Or did you already care about writing clean, well-structured code? And yes, I have a 3D of Super Mario dancing on my head now. Great question. The part of programming. I did program in my PhD thesis. I had to program quite a little bit because I created my own simulator. And I consider my PhD thesis to be the first time I did true programming. I used Python and I built dynamics simulator. What is that? Basically, you have equations that describe, for example, I know that this joint is at, there's a rotational joint here, is at this position. And I know that there's another joint here and it has this angle. So this next part will be at this position. And there's another joint and this part will be at this position. And these angles are all changing over time. They are moving, the robot is moving. Let's add a claw here at the end. The robot is moving, these angles are varying over time. They have a delta t, they have a time step. What I did, basically, in terms of programming was, I have the equations that define me where this point is based on this and this angle. I have the joint positions as an input. So I have joints as an input, then I have code, and then it gives me the body configuration. So I have joints, they go into a machine, and the code outputs the body configuration, and that happens for each time instant. Well, if you add on delta t, if you had iterations, if the simulation is advancing a long time, and you add, like, for example, position is equal to the current position. Okay, let's add an indicator. So x for time t plus 1 is equal to x of time t plus delta t, and this x with a point is velocity of t. So with this we can get the next position with the velocity, and we can get the next velocity equals to x. This is that. Oh no, that was correct. Next velocity is equal to the current velocity plus delta t times the acceleration. And basically, by running this over time, you have the robot moving, and then this is a lot of modules of programming. I had a module that created a display where I can see the robot moving. I had a module that was giving me the force for each joint. So I did a little bit of more serious programming in my PhD thesis. However, in terms of code, this is not that complex. It doesn't have like a lot of classes, a lot of ifs, a lot of user interaction. I'm using code as a tool to solve mathematics and using them to evolve along times. I used some libraries like NumPy. That's a lot for matrix calculations and things like that. So I did advanced programming for my field. If you're a programmer, this programming will not constitute a lot of issues for you. I even added a little bit of machine learning to the equation, but it wasn't that tricky. Did I have programming before? Yes. I had classes of programming in both high school high school and at university. Oh, wait, I'm writing in the spot. I'm writing the question. And at university. University. I had programming in both of them, and I can say that the programming I had in high school, in my case, was way better and more useful than the programming I had in university. I had one course of programming from which I had zero memory. I had another course of programming from which I have zero memory, and it's not even good or bad. I remember zero. I had another third course of programming for which I have bad memories. And then I had one course of programming that was great. Only one. So I had 4 courses of programming in my mechanical engineering degree. 2 of them, I remember absolutely nothing. I cannot tell if they were good, if they were bad. They have been erased from my mind. Zero. This one was a weird programming, which is programming based on images. It is very weird. You basically have blocks that connect, and you are programming like you have a button. For example, this block is a button, it's connecting to this variable, and this is maybe generating 2 variables, and this is a sum, and you are just programming. Things looked very ugly and very graphical, and you are programming by dragging blocks, and this is the type. This probably has a name. All programming that I was doing was like this, and then you had a cycle. Maybe it was going here. It was all time, and this is the bad memories. I don't remember learning a lot of useful stuff. The good programming class I had in university was computer vision. Computer vision, I remember, was awesome. I had a great time, and it was basically computer vision. Basically, you have a matrix, you have a webcam. It was learning, for example, I place a coin in a webcam and it tells me the value of the coin, like this is a 10 cent, reading text through cameras, detecting people or facial expressions. It was a more focused programming. It was not like generic programming. It's like, okay, you know the basis, even though we had no basis. You know the basis, now we're going to learn a specific application, and this was really fun. This one I learned. In high school is when I learned like regular programming, like writing code. It was in Visual Basic, I believe. We had to make, remember, one of the trickiest problems was making an Angry Birds game. And I have a fun story that I'm going to share from my high school programming. I'm just giving a lot of context, and I'll go to the question itself. We had a test in class. Let me go. Basically, we had, each one had our own computer. We were sitting here, another line, more people, and we had to solve a few coding things. We were sitting down, and the delivery of the text of the test was, the professor gave us a flash drive, a pen, and we copied our answers into the pen and then give it to the next person. What happened? Well, I was, let's say, here, down the production line, and then it comes here, and people knew I was a good student. So, some people, I passed my data into the pen, and some people just copied my program and changed the name to their name. And the professor was like, when the grades were released, it was like, okay, 5 tests have been considered null, they are void, because you copied, and mine was one of them. And I was like, no, professor, I haven't copied from anyone. He was like, oh, but there were other tests like yours. And I was like, okay, they copied from me. And the professor was like, oh, yeah. And I was like, no, your system of delivering the test was flawed. They can literally, I was explaining to the professor, they can literally just take the hard drive and copy my files. I wasn't complacent with the copy. It was done against my will. And he was like, oh, how do you know I didn't copy yours? And I was like, you can call anyone here. They will tell you that they copied from me. I'm the one who made this. I'm better than all of them. Being confident helps in these discussions. I'm better than all of them. This is my grade. What grade did I have? And then he was like, okay, you had 19.8 out of 20. And I was like, okay, give it to me and you can null the rest of them. And that's like the professor then confronted the others. No one backed away from my story, so I got the grade. But yes, in high school I was a good programmer yet. Yeah, confidence is necessary for these things. You will get nothing from saying, yeah, for being meek. People smell weakness, they attack, they pounce. In a thing like this, you need to be like, no, I'm good, I didn't copy. They did. I will not. It's not, maybe he was expecting something from the movies like, oh, we stand together, solidarity. Yeah, maybe I will defend my colleagues, I will not say. And I was like, no, they all cheated. I'm innocent. I will not defend anyone. Screw them. That was basically it. I'm kind. That's my philosophy in life. I'm kind when I should. When I shouldn't be kind, I'm. A lot of people think because I'm kind, I will let myself be taken for stupid. No, I will not let you take advantage of my kindness. I'm very strong-willed regard to that. So, was the first time you programmed during your thesis? I programmed before, but the real code for the first product, the first actual code was during my thesis. And what beginner mistake do you think you made at that stage? My mindset there was, as long as it works, it's fine. Kindness isn't the same as weakness. You did well. 100% Sumo. 100% agree. I have zero regrets over my attitude there. Zero regrets. A lot of what I did in programming was math and physics program. My code was known for being extremely ugly. For example, I have 4 files I need to load. File 1, file 2, file 3, file 4. A lot of people will just use any structure. I just had a variable, for example, I, and then I had if I equals 1, load file 1. If I equals 2, and a lot of programmers will look at this and they're like, no, you're comparing every single case for every single situation. This is so bad. Even if I equals 1, then if I equals 2 will run as well because you're not nesting things. A lot of my code did have things that are bad practices in programming, but at the same time, you need to think a lot of engineering is, what am I doing this for? Am I doing a product? Am I doing a finished product? Or am I testing things that I don't know if they will work, and I want answers as fast as possible? It was the second. A lot of methods that I tested, like mathematical methods, and these were long equations and all, I just realized that they didn't work for my problem. And if I was concerned about establishing good methodologies, good practices, I would have taken so long to produce things that whose destiny was the trash can. What ended up happening, and I have zero regrets, is that some parts of my code after testing started like, okay, this is now permanent, and then I rewrote this as more elegant. There was a stage where I felt the need to rewrite because things were so ugly, things were so chaotic, it was impossible to track, to navigate my own code. And at that point I was like, okay, but now I understand it better, time for a rewrite. I like the fact that I divided the testing from the optimization. I have zero regrets about that. My code was not clean, it was not well structured, but when it needed to be clean and well structured, I was able to do it. I still had a few flaws, but I have zero regrets over the approach I made. One nuance that I would like to add here is that programmers are peculiar creatures, and depending on the programmer that I ask for doubts, they can be your greatest friends or your greatest enemies. A lot of programmers are very bad at staying focused. Like, I will go to a programmer at I'm at this stage, I'm testing a very specific thing, and they're like, oh, you need to focus on this and that. I'm like, I do not care about this or that right now. I have a weak deadline. I do not care about this detail. And they're like, oh, but this can generate security vulnerabilities. I'm writing code for my own computer. Why do I care about security vulnerabilities? This is working on an offline machine locally by me, for me. Why do I care that people can inject vulnerabilities into my code? And I mean, they were right for their area. If they are producing a code that's going to be used and everything, they're absolutely right. I was doing things that are bad practices, but it is very important to separate your priorities. And it's funny because when I did this, when I did all of this ugly code, my main position would probably be of shame of my own code. If you ask me back then, are you doing the right thing? I would say no. Now that I finished it, now that I defend the methodology I did, I defend the wonky code I write, now that I have more confidence, I believe this was the best approach. With my lack of basis, with the problem I had at hand, with the time constraints, I believe that bad spaghetti code was the right answer. For my specific problem. It's not the right answer for everyone. But it is funny because if you asked me like a year ago, I would be more apologetic. I would be more like, okay, my code was very bad. I am sorry to all programmers out there. Now I'm more confrontational. I'm more like, it was bad, yes, but hey, I have a PhD. It worked. All the outputs were perfect. I can manage it. For example, an important thing of code is portability and understanding the code, like leaving comments for other users to continue the project. My code is a nightmare to read. I can understand it because I wrote it. It is horrible to read. My code is very flawed, but it completed its tasks perfectly. That's my approach to coding. If I do, and all of these mistakes that I made set me up in a position where I feel like when I have to code again, I will do it a lot better. So yes. I wanted to talk about coding in general. This question was just the gateway towards it. I was very, as long as it works, it's fine. I did not care about writing clean, well-structured code at all. And nowadays, I believe I can rewrite all of that code way more elegantly. It really depends on your process. Some people like to write it well the first time. Some people don't mind having to do rewrites and just focus on speed. Yeah, the problem is, the problem really, in my specific case, was because so much of it I didn't know if it was going to be useful at all. I would be wasting time on writing clean code for the trash. I think that was the main thing from my... I deleted so many pages of code, and I deleted them not because they were poorly written, because the mathematical processes, I basically reached a dead end. It's like, oh, this code, I cannot progress with this anymore. This code is good. This code has an application. This code... there's a reason why this code is in literature, but for my specific application, I didn't notice this flaw, and this flaw makes it so that all of this block is garbage. I think I had more... because I was quote-unquote innovating, I had more trial and error compared to regular... I think most programmers don't have that... I mean, programmers do have trial and error, but not at this level. Not at the level of the equation itself, the line itself. Like, you do not... You know what the button does. You do not have to understand, will a button work or not? You know what a button is. You click it, And depending if it's a toggle or something, it changes a value or something. These are more grounded things. I was working with physics that starts getting a little bit abstract, and most of my problems were not programming problems, they were mathematical and physical problems. Thanks for your answer, seems fair. Yeah, thank you, thank you. I navigated a lot, but I hope it helped. And I do agree as well on funny failure. If you want to write beautiful code for the garbage, it feels annoying, but some people need to operate like that. Some people they cannot produce like for a sense of pride, and I can be blamed on that in other areas, not in programming, but in other areas. Some people just can't haste it. If they try to haste, they will fail, they will fumble, they need to write a good code, and only then they can make the decision, and it doesn't mean that it was time wasted, it was just we have different minds, we have to operate differently. So next question. Where's my question slide button? Here it is. Anonymous. Why did I say anonymous like that? What was the first you ever designed? I'm going to assume it's first thing or machine, engineering or not. And I'm going to go to this question in 4 ways. I have 4 things that I design. I'm going to go for the first thing before uni. Okay, first one before uni. The first one in uni. The first thing that was more mechatronics. Can I ask you to judge on the design of the G604 mouse? Oh, I do not know that mouse. Let me check real quick. Let me just add one more to the list. Okay, let me... G604 mouse. I mean, looks... I nowadays mostly use vertical mouses because of hand injuries, but looks like a good clean design. I would have to spend more time thinking on it. Right now I'm addressing this question, but that's... I use these mice and I really like them and just want to know how good they are from mechanical engineering. Yeah, mouse design is a lot of ergonomics. Ergonomics is a very complex topic. It's how well does the mouse fit your hand. Things that are designed for human use have a lot of both mechanical engineering design and like design, like actual designers describing the curves, describing the surfaces. It was not my main area to design things to be held by humans. I think in that case, if you like how the mouse feels in your hand, I think that's the most important criteria. Like literally, I think nothing I could say about a mouse's design is more important than how it feels in your hand. Because that's a lot of engineering, is how well does it fulfill its function. If you buy your own mouse, the function is, I don't care if 100 people say it's comfortable, I care that it is comfortable for me. We all have different hands, hand sizes matter. There are mouse for people who use the left hand or right hand. Some people have more difficulty with articulation. Some people, for example, if you play first-person shooter games, you have your sensitivity low to increase your muscle memory because you want to move your arm a lot. If you play RTS, you have your sensitivity high, and that will also affect how you embrace your mouse. It has a bunch of macros and can use batteries instead of several internal lithium batteries that degrade over time. Yeah, that the feel is very important, but all of that sums up to create an important problem. Wait, what's the first thing you design? Oh, I'll get to there. I haven't started answering the question, do not worry. I got sidetracked. Also, I've been designing a PCB for a modular split ergo keyboard so that people can make their own more easily. Oh, I haven't tried a split ergo keyboard, but I'm very curious. And then I will do my first robot. I'm going to describe four machines here. My first but for university, I didn't have a lot of knowledge. It was in high school, I believe. It was something just very goofy. Me and my friend for a class project, we basically take the remote controlled car, like a standard remote car with the wheels. We removed as much weight as possible, so we removed the chassis and everything, made it just bare bones, and added some styrofoam wheels, like really big, proportional to the car. Like the car was like this, and they had pedals on it. The pedals were more like internal, like this. And we basically made, it did work, an amphibious car. We wanted to convert a remote controlled regular car into an amphibious car that could walk on water and land. It was very unstable, very wonky, very, like, not best materials. This was made of styrofoam wheels, but it did work. So this is not that cool of a marvel of engineering, but it is it was my first machine, and it already showed that my brain was leaning towards engineering. It was very goofy. So my first one, I would say it was the styrofoam hybrid car. Let me say hello to Felon. And would you rate the QWERTY layout? Specifically with mechanical keyboard in mind. Oh, I don't... I feel like any layout will always have their strengths and disadvantages. I feel like hating on QWERTY nowadays is just a trend. I know that theoretically speaking, if you optimize learning another keyboard layout, you can be like X% faster and things like that. But I would need more data. For example, is moving your hands in that other keyboard more prone to injury and things like that? Typing speed is not the only thing. So I would need to conduct a lot of research on that topic in particular. So in university, my first machine was way more elegant. Way more elegant. I like it a lot more. And it was using one of my favorite mechanisms of all time, which is the slider crank mechanism. What was our goal? We had to build a machine in uni where we have a bucket. We have some distance. I don't remember the exact distance. We have a table. And from the top of this table, we have a ping pong ball. We have to throw ping pong ball into the bucket with as much accuracy as possible. We want it to be replicable. We want it to hit the bucket every single time. And I used one of my favorite mechanisms, which is the slider crank mechanism. What is a slider crank mechanism? You have a revolute joint here. You have one bar. Okay, this is the ground. You have a bar here. You have another bar. So this is rotating. And here you have a slider. So how these mechanisms work is that you will be rotating. This will be going... This bar will be going back and forth. And this will go in this direction. So this converts rotation into linear motion. And you're thinking, okay, how does this... How the frick does this work to throw ping pong balls? There is something we can do in mechanism design that is called inverting a mechanism. If I could copy and paste that mechanism and I'll rotate it like this, what you have here, instead of having this as the actuator, this would be body 2. Oh, wrong tool. which is the body being actuated. Body 1 is the ground, body 3 is this bar, and body 4 will be the slider. Now this is our body 2. We are controlling this, we are moving this up and down, and this goes in this direction, and this is how an umbrella opens. You can extend this bar here, and this is literally how an umbrella opens and closes. You put this down, this becomes, if you close it, this becomes like this. So this bar becomes concentric, and this becomes like this. All of this becomes a line. And if you open it, this goes up, and you have your umbrella like this, and this is, you have a slider crack mechanism when you are controlling like a bunch of bars from this single slider. This is how you open and close an umbrella. What we did in that group project was even a different type of inversion, because we wanted, some people used rope, some people used the springs, but our main requirement was consistency. We want this mechanism, okay, didn't copy everything. We want this mechanism to be consistent. That was our main thing. And what's consistent? Gravity. Gravity is quite consistent, and we did this inversion, but we changed the starting position of the mechanism. Let me draw it. Wait, was it that inversion? No, it wasn't that. Wait, I'm thinking, because I want this to go up. It was... Oops. How did I decide? It was a ping pong ball thrower. Wait, why is this being so wonky? Because when this went down, that bar went up. Oh! I don't know. How did I design my own mechanism? So this goes down with weight. I remember that this body goes down. Oops, wrong brush. Let's add one part of a time. And this going down will pull the bar. One bar down and another bar up. Sorry, I'm pulling a blank. Oh, the first machine I designed, very elegant. So elegant that I don't even remember how it worked. No, I don't have it in another room. Another colleague of mine saved it. Okay, I think I remember. It was upside down. And when this goes down, it was not exactly this, but imagine that you have sorry, wrong brushes. You have this being longer, and with a basket and a ping pong ball here. And this just went down with the weight of gravity. So, oh, wait. This went down with the weight of gravity, and this going down. Okay. Oh, this is the end of motion. Okay. That's it. This went down. And when this started like upright, and this going down would make this go whoop like a catapult, and it would throw the ping pong ball. And since it's all gravity and things like that, we just needed to adjust our weight to adjust the actuation force, so it's very easy to add or remove weight, and it would toss the ball every single time into the bucket. That was my first machine in the as a mechanical engineer. Exactly, extend the other lever. Hello, Emperor Armpits, welcome. We are talking engineering. I'm asking this because I'm pulling an all-nighter studying right now. Beat out, but how you rate the design of the human spine? Okay, anything in the human body with the lack of some minor exceptions. If you go to a scale to evaluate engineering products from a 1 to 10, where 10 is like the best engineering product we have, most things in the human body are like 100. They are way more complex than what we can achieve in engineering. It is insanely complex. People are like, oh, they get damaged, they have flaws, and I'm like, it's like a smartphone. Like, yeah, the spine gets damaged, but it's conducting electrical signals, it's doing so much complicated stuff, it's articulated, it's a lot of connections at the same time. Like, yes, they are flawed, but have you seen what they are doing at the same time? It's insane, the level of degrees of freedom and everything. So most things of the human body, I will rate them very high. My first mechatronics project, this one I can describe better, was the Chichomtro. Metro comes from metrology, the science of measuring stuff. So it is a measuring device. And Chicho, it's the nickname that me and my two friends called our professor. His name was not Chicho, but we called him Chicho. He doesn't know we call him Chicho, no one knows we call him Chicho. And the Chichomtru was the... oh, not Chicho, Chichas. And the Chichomtru was the measuring machine we made for Chichas. That's our name. And this was very simple. It was a box. This was made in conjunction with our knowledge from the machine vision. It was a box with controlled lighting. So we had a lamp. And then we had some acrylic panels that we scraped so it became diffusing. It diffused the light. We didn't want focus light. We have light on top being diffused. And we have a smartphone holder here, a smartphone holder here. And what this did is you placed, for example, a gear. It was very good at measuring gears. You placed a gear inside. Let me try to draw a gear. I mean, this is not a correctly drawn gear, but works. And it would tell you, for example, with computer vision, things were calibrated. It will tell, okay, this is a 3mm modulus gear with like, this is millimeter, with like 26mm thickness, 28 teeth, and things like that. We basically developed the software where we placed a lot of standardized mechanical engineering components. Like, it also worked well with nuts. We calibrated it and it's like, oh, is this an M3 or an M4 nut? You place it inside the Chichomtru and the Chichomtru will tell you immediately. Of course, not that convenient. It was more something, it was literally a university project, but it did work. And it was cool. It made us feel cool to design something like this and see it work. I don't know how much application it would have because most places just have labeling systems, they have methodologies. Like, you don't often come across the specific problem of, oh, I have 20 nuts that are M6 and 20 that are M8. I need to evaluate them quickly. It's not a standard problem, but we did create the Chichomtru and it did work. So nice to know your perspective on the human body. Thanks for asking. I'm sometimes alternating between the questions people ask before them and the questions on the chat. But thank you for asking questions. So this was the first machine in mechatronics. My first robot was basically a robot. Oh, let me go up here. that had a rotating base, and this was really cool because we had the batteries on, like the batteries were here, and we have a 360 connector to guarantee that the batteries could still power the top even if this base rotated 360 degrees. Continuous rotation, that's more complex. If you have limited rotation, cables don't get tangled. This had particular connectors, and it was rotating. We can keep rotating the top part non-stop. Then it had one arm, two arms, and a claw, and it had a thing like this and a camera. And what this did, it also had some LEDs for visual connection. The camera detected depth and colors. What this does is that we placed some cans, and it will detect, for example, this is a Coca-Cola. LED will turn red to indicate it. It would grab the Coca-Cola and then place the Coca-Cola in the Coca-Cola place. Same for a Fanta bottle. So this was my first robot. We built it. This part was made of wood. I think these were aluminum bars. We actually like cut the wood, like we literally built it. And it was a robot to detect cans and move them from one place to another, and it worked. Like it scanned, if it was detecting any can, it scanned like 360, found a can, pick it up, put him in place. This was my first robot. And it was really fun to work with in this. Okay, yeah, this is better. So yeah, this was question number 13. Not 13 of today, 13 overall from Mr. Anonymous. Thank you very much for the question. That allowed me to yap quite a bit. Let me just check one thing real quick before I move on to the next question. Can picking bot, exactly. Was that can picking bot? Next question, we have Fallon asked this in chat the other time around and I didn't have time to address it. How much of mechanical engineering is memorization versus intuition versus researching what's been done versus creating something new? Okay, I think first of all, it really depends on your field. Depends is the worst answer ever, but it's true. And there is a difference between education and working. Because I would say, for example, the memorization part for education, quite a bit. For working, almost zero. You will not have to memorize by, like, do an effort of memorization. You'll just work with something so often that they will become a part of your memory. I think most things you memorize in working, you memorize them naturally. A lot of engineering, a lot of work, you have to consult a lot of catalogs and check things. You have mental references, you have mental pointers. You know, for example, oh, if I want to select a bevel gear, I will have to do those 3 or 4 equations. But you don't remember the 3 or 4 equations. And you know that there are some catalogs. You know that, okay, this is strong, so maybe steel will be a good material, maybe titanium. But you will check. You will need no memory of these things. You have some pointers. I think in most works in mechanical engineering, memorization, you use it because you absorb information and you use it to make things faster for you. Versus intuition, I think intuition plays more of a role. I think you need to develop that intuition of knowing. A lot of people, when I started working with newer engineers, they were like, oh, this will need a bearing when I was designing a robot. And they're like, oh, why do you think it's going to need a bearing? And I'm like, oh, because I've done this before and I know it needs bearings. You develop a lot of that intuition. What's the theoretical knowledge? And a cool thing, for example, one of the areas which is metal smelting, And when you're producing parts by smelting, you have like a hole there. You're pouring liquid metal. And like this has a mold. And there's a lot of flaws that can happen. It's very easy for parts to become messed up in liquid metal pouring. For example, one that's very, I mean, not very obvious is that material can contract and then you have that shape and then suddenly the material contracted and you have like a gap here that wasn't in the mold. It was the material on the inside contracted later, and the material from the outside had to go in to fill in the contraction of material. It depends on the... You have something called a feeder. Oh, okay, I need to not get lost in smelting. What you do usually is that since you need material, you get this part, like this shape, and you smelt not this, but you add un alimentador, a thing like this, and you make sure that this is going to be the last part to solidify. And what happens is that all of this is like still liquid and solidifying. And since this is the last part to solidify, you're going to have this metal will flow down, and then at the end you'll have a hollow here. But this is not a part of your main part. You cut this out, this goes off, and then you have your perfect part. You have parts of the foundry that are just to be removed. But sometimes you do all the calculations well, and the part still comes with a flaw. And what you do is that you do not use theory, you keep pouring, you keep testing things, and you see what works. Basically, you learn to recognize signs. Like, oh, maybe there's a lot of holes. Oh, this is because of that. Oh, this is because of the metal mixture. And you just go trial and error. And I remember there was a case in a factory where all engineers weren't being able to pour this part. And one of the workers said, oh, why don't we try pouring it with the mold like this instead of the regular shape? And people were like, there's no reason for that to work, but we've tried anything, let's try it. And it works, and now they always pour that specific part like this. And this is pure intuition. This is not memorization. What's been done versus creating something new. Now, this is the part where I have to be real and say that most engineers want to create something new, but I think most engineers will not be creating something new. I think most engineers will be researching what was done and optimizing what was done. Like making something that produces 101 megajoules, you change the design and now it produces 102 megajoules. You want to install an AVAC installation, you're not inventing a new AVAC system. You're just going through the formulas and applying knowledge that has been accumulated from the past. I think most people are not creating new things. I think some engineers are developing new products. I think they are the minority. Optimization is so important, true. I think most engineers are, some are optimizing, but I think the majority are just doing what has been done a lot of times before, but has its amount of know-how. For example, you need to know the equations to pick an air conditioner. They are doing, a lot of engineers are doing what has been done a lot of times before, but they have the qualifications to do it. I think this is what the majority of engineers are doing. They are doing maintenance, for example, they are following maintenance guidelines. They are not inventing new maintenance guidelines. They are getting familiar with the system and following the guidelines. They're following the systems. They're following code. They're following standardization. Most engineers are not creating stuff. I feel like if you want to create stuff, a PhD is a good chance, or some research-focused companies. Okay, how much of your mechanical engineering work was rated on hand drawing ability? I would say hand drawing ability, I would rate it at like a 0 or a 1 out of 10. Material science, I need some, but the basics was enough. Other physics, a little bit. For my area in particular, for mine, a lot of dynamics, a lot of how forces and torques affect accelerations and angular accelerations and things like that. Maths, I would say very basic. I would say trigonometry to a certain degree, matrix like algebra, but my high school mathematics were really complex. I would say that my university mathematics as an engineer were simpler than what I did in high school. Computing, I did quite a lot of computing. And CAD, I did a lot of CAD. Other skills, knowledge. In my work in particular, yeah, CAD was a lot of... And mechanism does... like design of things were a big part. And in that specific knowledge, I would say, like, knowing systems. Like, for example, knowing what a bearing is, knowing lubrication, knowing... some of these things are basics, but the basics are so wide. Isn't inverse kinematic a bit complex? Oh yeah, inverse kinematic, that's a good one. And hello, Math Magician. It is fun. It is fun. It is quite complicated, but for my work in particular, I learned inverse mathematics. So in courses, that was probably one of the most advanced mathematics I did in university. In my project for robotics, I never used inverse kinematic, at least not in that shape. I developed the recursive algorithm, which is basically you just have an equation, you have inputs, like 3 variables, x, a, b, that go into this equation, and you have, for example, bar A, you apply this equation to bar A, and you have its kinematics. Then you have bar B, and you apply the same equation, but now variables x, a, and b are different, and now you have bar B, and it doesn't matter. While in regular handmade inverse kinematics, for example, this would be a nightmare to calculate the more bars. Here, you add another bar, you just add one more equation. This was forward kinematics, I believe. And for inverse kinematics, I think I dealt more with machine learning. So those long equations, for example, solving the what's the name of Lagrange equations of motion. Okay, that was probably Lagrange equations of motion. This is the most complex mathematic I did, by far. If you Google Lagrange equations of motion and see some examples, these get really tricky. These basically work with the balance of energies, how like kinetic energy is transforming into potential gravitic energy and things like that, but it also involves kinematics and motion, and these can get out of control really fast. So in theoretical, like the classroom, I used a lot of complex mathematics. In my actual project, like my PhD, I didn't use that complex of mathematics. But yes, during this side quest, I think I answered quite a bit of Fallon's question. More intuition than memorization, in my opinion. Researching what's been done is huge, in my opinion, and I think a lot of engineers should do it more. I hate doing it. I mean, I hate and love doing it. If it's interesting, I love doing it. If it's not, and sometimes you'll have to research what's been done in a very uninteresting field. But like in robotics, it is cool to research what's been done. And creating something new, I would say that's the minority. Let's go. Let me hydrate first. Ta-da. Johnny FFG. Is it true that fluid mechanics are the most complex? Why? Second, okay, let's do one question at a time. Is it true that fluid mechanics are the most complex? Why? I think they are some of the most complex. I think there's one that's more complex, but some people, it starts threading the edge between mechanical engineering and like physics and everything, which is quantum mechanics. I think these are worse. And for example, if you're studying, I studied a little bit of Hamiltonian mechanics and things like that, quantum mechanics are worse. But I think fluid mechanics in the field of mechanical engineer, like pure mechanical engineer, I think they are some of the most complex. And the question of why is really interesting. I think one of the reasons why it's so complex, it's about intuition. You take a ruler, like a wooden ruler in front of you. You bend it, it breaks. Congratulations, you've learned about how bending stress works. You take a bouncing ball, you throw it against a wall, it bounces back. Congratulations, you're learning impact, you're learning like a lot of physics and solids mechanics are very complex, but we interact with them since the day we are born. And because of that, they are very close to... they're very intuitive. You just add a little bit of mathematics to it, a little bit of spice, and you can go different levels. For example, modeling a collision can be very simple. It can be like, oh, it's just a little bit of energy loss. Or it can be like, no, I want to model each section, how much there is like penetration, deformation between the two objects and things like that. But the basis for those collisions are things that are intuitive for us as humans. We are interacting with a lot of solids. Even though we interact with a lot of liquids as well, we mostly interact with water, and not in a lot of complex ways. We have water stored in reservoirs, we have water stored under pressure, and we open taps, and so it flows because it's under pressure. But there's not, like, you are not dealing with a lot of fluids. And by the way, fluids, I just want to say to people that fluids are liquids and gases. One interesting way, for example, fluid mechanics is often deeply related to thermodynamics. When you put your hand out of your car, it gets fresher, even though the air is at the same temperature, if you're speeding or not. But if you're going fast, it gets fresher. That's because we have convection heat transfer, and convection heat transfer is proportional to velocity. So you have there one thermodynamic principle that is intuitive. You have some. Another that is weird is that when we talk about, I think it's Bernoulli's equations that balance pressures of fluids. When you have one of those pools and they have these water jets, if you've put your hand near one of these water jets, let me draw a hand. You've probably felt like this is pushing your hand, but at the same time, you kind of feel like your hand is being sucked in. You feel a weird thing, your hand is like around the surface, and you're like, you're getting pushed, but at the same time, in some points, you're getting sucked in. And the reason is we have three pressures. One is gravity, basically how low you are in the fluid, and then you have static pressure and dynamic pressure. And dynamic pressure has to do with the velocity. And all pressures in a fluid try to find balance. So what happens is we have here dynamic pressure that is going high because of the velocity, and we want to find a balance, so static pressure goes down. So, and static pressure going down, that's void. And void sucks. Void literally sucks. So, because there's a lack of... there's low static pressure, there's lack of particles, your hand wants to fill the void, and it gets sucked by those static pressure. And that happens in, like... that's how planes fly, that's how aerodynamics work. It's always these three things. And fluid dynamics with entropy equation. Yes, there's entropy. I think another reason why the fluids are bad is that you have rubber, a rubber ball, and it behaves in a certain way. You have a steel pipe, it behaves in a different way. but in a lot of ways, things don't change that much in the scales that we work with. If you go micro, or if you go macro, blah, 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 they can change, but in most of your applications, it's not changing. In fluids, you have like regular fluids and non-Newtonian fluids. You have like micro things or macro things. You have regular flow or you have turbulent flow. And there's so many conditions that it's like, okay, if this changes, now all of your equations change. If this is thick, it's these equations, now this is thin, different equations. And I feel like there's so much variability to the problem, so much things that will change the nature of your problem. And we are working with things that we aren't intuitive in our day-to-day basis. And I think that's what makes fluid mechanics so much more complex than solid mechanics. It's how variable the problems are and how non-intuitive they are for our day-to-day life. I think it's a mix of both. Void sucks quite. Yeah, I remember thermodynamics for me was not the hardest of courses because the professors literally said, oh, this course can easily become the hardest of courses for you. I will make it so that it's not that hard. Most of you will pass, you just need to understand the basics. I don't want to torture you. But a lot of these topics are like an endless bottom where you can just keep adding more and more complexity to it. And I think that's the reason why fluid dynamics are so complicated. And a lot of these equations, for example, you have a solid, you want to program their deformation in a computer. What you do is that you divide a solid into small elements and you're like, okay, these elements are doing interaction. They're easy to solve computationally. Computational fluid mechanics, there's the Navier-Stokes equation. Like, there's so much things that can go on, so many phenomenons, and the equations are not simple that it just becomes a nightmare. So I think I agree that fluid mechanics are probably one of the most complex topics. One, because how broad they are, how easy they are to change, how much equations they have, and how our tools to deal with them are not that good, and how non-intuitive they are. And fluid mechanics is amazing. It is not my area, but it is one of the coolest areas. I agree. Jotaro Star. Okay, and second, to train robots that behave like humans, why don't they simply create bodysuits full of sensors for people to wear during the day to generate training data for robotics models? That is a great question, and that is a question that I, during my PhD research, stumbled upon by accident. Not this specific thing, but one of the answers to that. Which is, for example, if I'm building a humanoid robot, we have... Okay, when we're building a manipulator, I'm going to introduce the concept of redundancy. I want to reach this point. That's my goal. And this is a top view of a 2D problem. I create a revolute joint here, and a bar like this. And here is the claw. That's not that good of a claw. Here is the robotic claw. I want to reach this point. What do? I rotate around this. My hand, the new position is this. I've reached this. Perfect. However, now there's a pillar here, and there's a pillar here. How can this manipulator reach that point? If it goes here, it collides. If it goes the other way around, it collides with this pillar. It is impossible. We have obstacles. We'll never reach this because this manipulator has no redundancy. What is redundancy? Redundancy is having more than one way to reach the same point. And you do that by adding degrees of freedom. If instead of this manipulator now, I have a manipulator that's like this, another bar like this, and another bar like this. This has more redundancy. It's still a serial manipulator, but with more degrees of freedom. And now, the previous one could reach that point, but this one can reach by rotating this and rotating that. and it can go around the obstacle. It can reach this point in many more ways. And the more links we add, like we can break this into 2 links, we are adding like it can reach limitless amounts of configurations you can have to reach the same point. And in robots, this is very important. More degrees of freedom means more efficiency, means we can reach things better, but it also means more motors. We need a motor to control each of these. Motors mean more weight means more energy consumption, and this starts snowballing and increasing the complexity of your robot. Oh, let me check what fellas said. Robots from humans with sensors, they're trying that now with humans using VR headsets and sensors with neural networks being trained, but it's still not advanced enough. Yes, and I'm good. I will touch 2 or 3 problems of that. And most researchers have come to a model of the arm. They want to mimic the human arm, humanoid robots as we are talking, and they have come to a model of the arm. If I remember, I don't remember exactly what the degrees of freedom are. This is the shoulder, rotation, that, and then I think it's like one of these, and one of these. I don't remember if these are the exact joints, but most humanoid robots use 6 degrees of freedom for the arm, that's the number of joints, or 7. 7 is also common. However, for example, here the shoulder is fixed. Our shoulder moves. Anyone that's moving, like this has been studied by kinematics people and everything. The movement of our arms starts like in the center of our chest. This is a complex kinematic chain. And we need 13 degrees of freedom to mimic the motion of a human arm. So if we are training robots to move like humans, they need to be able to move like humans. Or else the training data, it's going to be like, move to that position. Oh, I can't. Because and it starts creating errors that propagate. So if you just try to mimic a one-to-one, you have to increase a lot the complexity of the robots because robots don't move like humans. That's reason number 1. Is that almost no robot moves like a human. I think that's the main reason. For training, there is advantages to this, which is how intuitive it is. We know how humans move. One thing that's really popular is, we call it teach by demonstration, which is kind of adjacent, but more mainstream. This is something that is actually like common. And you're literally like, you want a robot to move a can, for example, from here to there. And what you do is you set your motors to a passive mode and you literally grab the arm as a human. You grab the arm and you move the arm into the position. And you press a button that says like safe position. And then you once again, you pick up the arm, you are literally moving it with your hands and put it here. And you press safe position. And the robot will learn this movement and you're doing... Someone did the trajectory programming beforehand, someone did the tricky stuff. You're just moving it and it's recording, and then the robot will be like, okay, what, you want me to do this? And you're like, yes, do this 2 million times. And the robot will repeat, doo, 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 which is a good way, an intuitive way. Things being intuitive is very powerful in engineering. Another thing is also the amount of data. I know that for computer vision, for example, their main problem sometimes is not generating data in a lot of applications, is how can we have less data? A lot of images, like you have a 124 by 124 image. A lot of images, like if you have 2 million, for example, required for learning, a lot of these images are actually converted to like a 56 by 66 resolution. Times 3 for color. True. Yes, exactly. For the beep maps and everything, and sometimes they go if they can, they find other ways to program color or go for simple codes. In a lot of robotics applications, I think the main problem is not how can we get more data, is how can we get efficient data. So I think that's another reason. I think the person using bodysuits full of sensors, and nowadays with a lot of technologies, for example, I'm a VTuber, hello, a lot of VTubers use 3D tracking. I could easily see like companies being like, okay, do you agree with getting your data collected for robot training? I mean, because of the keyword AI, I feel like a lot of VTubers will be unhappy because of the artistic side of generative AI, not this side of generative of AI, but because of the keyword. But I could easily see domestic applications of motion cap sensors, like movies use a lot of mocap technology right now. I could easily see a data center being like, okay, you are doing mocap for this Hollywood production, can we get your points, please? I can see that happening. But yes, I think this area is, I was just listening to a noise, is ongoing. So that's rain? It's raining a lot. Okay, if my stream goes down, I'm sorry. Portugal has been stormy lately. I hope we can stay together till the end. That sounds very dramatic. But if the stream goes down, I apologize. Nothing I can do. But I believe this question 2 is a question that is shifting. I feel like people are working on it. I feel like this is the kind of thing that probably there are research teams tackling that as we speak. And being like, that streamer, Nando, he's talking about our project, but he doesn't know us yet. It's funny, once you get into the world of engineering, for example, one thing that I don't think it's very popular in everyday talk, in like your talk, thinking about robots, you don't think about it that much, but I see it a lot in scientific conference, is swarm robots. I've seen so many research. There are simulators, computer simulators, focused only on swarm robotics. There's so many people working on swarm robotics. It's insane. I feel like if I talk with a regular person and I talk robots, like swarm robots is not the first or second or third or fourth or fifth or sixth thing that would come to mind. But swarm robots is something that a lot of people work on. Like a lot of a lot of little robots that work together to complete a task. There's so many researchers working on this. Every time I went to a scientific conference in the field of robotics, there were at least 6-7 presentations on swarm robotics. Some of them were really cool, others were boring, but that goes for all areas. Swarm robotics are a trendy topic in robotics, in my opinion. 6-7. This one was, I love sneaking 6-7s in. I've been sneaking 6-7s everywhere. This one was not on purpose. The 6-7 is taking over me. This one was not intentional. This was not an intentional 6-7. I did that video, I don't know if everyone saw it. I did a video where I'm like, oh, my channel, things are changing. I've been noticing for the past 6-7 weeks. And I was like, I was containing myself to not laugh at the 6-7. I hope by the way, I don't say this to every single question, but I hope I'm providing good answers to the questions. Oh, gee, I did not notice that one, but I did say 6-7. I'm like, yeah, I noticed something changing on my channel for the last 6-7 weeks. It's so natural. I hope I'm providing good answers for each question. I do try to take my time. I deviate a little bit, but I feel like that's a part of providing a complete answer. I feel like the journey and talking about adjacent topics is important to provide a full answer. This one, how useless in engineering, not is, how useless in engineering. I don't think I'm going to spend a lot of time on this question. And engineering is so useless that whoever wrote this, Mr. Anonymous, was using engineering, products of engineering, to write this question. I'm reading this question because of products of engineering. You're watching my stream because you're using products of engineering. Yeah, this is the best question. I don't know if it was meant in an ill spirit, like engineers, or if it was meant in a cheerful one. I think in a cheerful way, because I do believe engineering can be useless. For example, sometimes in product development, I love cooking, and kitchen is probably the worst and best place for engineering. Last stream, someone asked, what do you think is the most engineered thing? And I stumbled to have an answer. The most over-engineered junk you can find is in the kitchen. The best engineered machines you can find are in the kitchen. Kitchens are amazing. They have so much cool stuff, but also you see online those ads. It's like, oh, this is a automatic egg slicer, or the freaking memes of the dumpling machine or something. Yeah, kitchen is probably where you see worst and best engineering. But yeah, you look around you, there's walls. Civil engineer probably did the norms that get those walls. If he didn't, probably the construction worker used the cement mix, and engineers were related in the writing of the norms of those cement mixes. Have bolts. Bolts are products of standardization. I look around my room. That's made of aluminum. That aluminum thing was probably made by cutting a sheet of aluminum, then bending it to increase the resistance. Like, engineering, people used to say nature is all around you. It is true, but if you are inside your room and you look around, you'll see more engineering than nature. I just missed my question. Hello Johnny, we'll watch in the vault. Thank you for answering. I had a great time answering your question. Oh, has someone who works in construction engineering make things uselessly harder without any benefit very frequently, at least for my side of things? I would say, and hello Delanar, I would say sometimes it has a bigger picture. For example, sometimes things are done in a certain way and you don't understand them, and then things go wrong and you're like, oh, that's why it happened. I do have to say, I don't know if you're American or European, because I've heard a lot of horrible, like, laws and rules and everything when it comes to American constructions. So if you're an American civil engineer, that's a struggle. I'm not a civil engineer, but I'm on Europe. I think there's a lot of codes and everything, and there was a channel that was quite trendy, and he was showing how a lot of quote-unquote great things, great constructions, are not up to standard. It's like, oh, look at this building, it's beautiful and everything. You couldn't build it nowadays because it's not up to code. Like, the railings need to be this tall. And I would say that's not engineering making things more complex. That's lawmakers and administrators making things more complex, and then engineers having to follow it. Oh, and things being over-engineered. Oh, yeah. Over-engineering is also... I think it's becoming more and more of a trend. Sometimes there is a need, and sometimes... Okay, I have a great example. You have a block, and you want to machine it. And I've seen, and you want to remove like this part. And you send a technical drawing to industry that is like this. And doing this corner, doing this vertex in particular, can be very tricky. If you want this to be a perfect vertex like this, and you want this to have like 90 degrees angle, depending on the material, this can be extremely tricky. You have a machine, for example, a rotating machine that goes here, but you go with a machine like this and it gives leaves a gap here, then you go in this direction, and you will have always like a fillet in this corner. This corner, depending on the material, this can be a fillet that you cannot address. How can you address it? For example, you can have one of the faces, instead of joining to the corner, you dig a bit in, and then you go like this, and you allow the drill to dig into the material, and you just want another part to go up against this wall, up against this wall, and up against this wall, so this doesn't damage the structural integrity at all. So, having this as a perfect 90-degree angle with a perfect corner is over-engineering. And I've seen people do this, and they are not over-engineering due to over-complexity or something. They're over-engineering due to incompetence, due to lack of knowledge. I see sometimes over-engineering is born from ambition, born from desire, but there's a lot of over-engineering that is born from lack of knowledge. It's people who should have studied, and I think this is a trend that is increasing. A lot of engineers, I worked in a metal workshop for a lot of time. A lot of engineers never seen a tool, and they sometimes give you a project that is so complex, and they have no idea how complex what they are asking is. Questions in the way, Nando. Oh, sorry. They have no idea how complex it is. But of course, every case is a case. It could be laws. It could be incompetence. It could be trying to profit, like reinventing the wheel for the millionth time, just to... I mean, sometimes reinventing, like omnidirectional wheels are a reinvention of the wheel, but they are useful, very useful for indoors navigation. But a lot of people are market driven. Yeah, there's also, like, there's a distinction between good and bad engineering. I would say good engineering is never useless. I would say a lot of over engineering and stuff is bad engineering, and I think there's a lot of useless engineering. I agree. I will not fight you on that. I 100% agree. And that uselessness can have several causes. Lack of information, market, and so on. I hope I addressed that. And yeah, I do believe in, like, America and Europe are very different in many ways. I just noticed from videos online, I do believe that there's a lot of weird stuff when it comes to civil engineering in America. But that's not my opinion. That's an expert. I don't have enough contact and with American civil engineering. That's just me relaying content I've seen. Yeah, people feel the need to flex, and as I said to Fallon in his question here, I think most engineers want to create something new, but most engineers are at a job where they can't, and some of it can come from frustration. Yeah, I mean utilities, and they have wanted like 6 forms of restraint on a single run of pipe. Yeah, utilities, like drainage engineering and things like that. I think it's those areas have some of the best and worst professionals. From my contact, you have insanely good, like, people who are so efficient, and also people who aren't. Will engineer become more useless the more engineers there are? I don't think so. I think engineering will be equally useful. I think maybe engineers will have less good jobs. Yeah, engineering is doing natural selection. True, true, true. And I didn't. Let me say hello to Sugi Yamagawa. I don't know if I said explicitly hello, but hello, hello. Next question. Oh, this one from Lady. Is there good software for beginner developing robot? That question is very hard to answer, because one of the cornerstones of robotics, one of the things that makes robotics so complex, is that it's one of the most multidisciplinary areas there are. You have so many things that go into robotics. You have like kinematics. Okay, now this is too big. You can go for example, mechanics, electronics, informatics. Here you have, for example, position. You can have decision making. In mechanics, you have actuator selection, structure. In electronics, you have like power. You have like the sensoring, yada yada yada. And so when you ask me what's the good software for developing robots, these robots are all of these. I don't know what software you would need. For example, if you are talking about, okay, I have some parts and I want to control it, probably get an Arduino, an Arduino board, get whatever electronics components are needed, and the software you would need would be the software related to program the Arduino. That will be your, if you like want to go for Robotics 101 starting from scratch, Pro Micro NRF 54R. Oh, I have, this is not my, I'm robotics, but this is not my area. I will have to trust you. My area, I know this for simulation, and I know this. For example, for mechanics, one of the main softwares you need is a CAD software, and my favorite is Inventor. But that's paid. I had licenses because of my student status, so probably would get like something like Fusion 360. And for informatics, for what I do in particular, I used Python, and the software, like Python is not a software, I used PyCharm. And there's also MATLAB that's quite used in this particular field. But for a lot of what people do in electronics, for example, a lot of controller things, a lot of electronics, they would be different softwares. So I think it's very hard. I know, sir, the white stuff is in the way. It's less in the way now. It's not covering anything that dramatic. Let me see what chat was saying. It's a water line, so it's pressurized, and 2 and 3 forms is normal, but 6 is absurd anxiety of your stuff falling and blamed on your bad skills and not knowing what you're doing, which I feel like is kind of true. They want that much. Yeah. No, Star TV, but I do thank you either way. You've been supporting me a lot lately, so I do appreciate it. And Funny Failure as well, Karen Dost as well. Cool to see so many people. Sugi Yamagawa, Jotaro. Delanar, I've also seen Delanar quite a bit. Of course, I will not say every single name because I'm bound to forget one or two. But yes, this is a tough question, because developing robots is too much of an interdisciplinary thing. What a lot of robotics team does is that they have some elements and they know enough of each software to communicate with each other, but MATLAB is paid. Oh, I think MATLAB is probably paid. I also had license in university, so these two are the ones I use the most now because I'm no longer in university, and they can be used for a lot of things related to robotics, and they're both free. This for programming, this for CAD, for design itself. But what I would do, if you want to start robotics, I would try to find like a starter kit. There's often some robots like starter car, for example, and it's a car and it has some controls and it comes with its own software and things like that. If you are starting from somewhere, get a starter kit. I think it is so vast. Either get a team, get instruction from someone who knows already, or get a starter kit and work your way up from there. Yeah, university is probably the best place to learn all of this. I would say university. In some high schools and elementary schools, there are great robotics clubs. And you can start your journey there, but once you get to university, most universities will have all of this knowledge. Choosing a good one is important. Yes. And that's a whole big topic. Depends on your area, depends on your aspirations, depends on so much things. That's a whole topic. What is choosing a good uni? And some unis can be good on some areas and bad in others. So things also change over time. Maybe this university was good 50 years ago, but now it's bad. That is a whole big topic. Okay, big question. Okay, na question this. Mechanical engineer with a master's here, who left a career due to challenging my own core beliefs, values, and felt confident enough to quit and pursue something I can feel good about. I have played with the idea of pursuing a PhD during this intermediary period, but don't know if what idea of mine is worth the pursuit. How did you commit to what you studied in your postgrad? What frame of mind, what questions did you ask yourself that gave you the confidence to pursue it? This is a big question, so I'll tackle it by part. Okay, oh, let me just check if I missed something. Okay. I was checking my notes from the previous answer. The first thing I want to talk a little bit about I'm a mechanical engineer who left a career due to challenging my own core beliefs, felt confident enough to quit. I feel like if it was challenging your core beliefs and you were confident to quit, I think no one can judge your decision. You know your conditions better than yourself, but I can just support it. I feel like if this was how you felt, that it was challenging your core beliefs and things like that, I think the more you stayed there, the worse things would get. I think they would just get worse and worse, so I think it was the right call. And I want to say that this is a problem that can happen in all areas. This is not like, oh, I'm a mechanical engineer, now I'm doing something unethical. Mechanical engineers have so many areas, like I've talked about friends who worked in the butchering business, and that can be, if you're a vegan, this is not this is not your favorite business. But I have friends who worked in farming, and a lot of what they did in farming as mechanical engineers was eco-friendly farming, for example. Another thing, for example, you can work in industry automation, and the same work can be, for example, remove hazard. That's something you can do in automation. For example, coal miner don't have to go mine coal anymore, or you can just make people out of jobs, and that will become more case by case. Or for example, medical is a great field for mechanical engineers to make a huge difference. like rehabilitation devices. I thought the other day I know people who worked in stents, which are devices made to dilate veins that are clogging. So in mechanical engineering you can have a lot of, but inside of medical you can also be doing some things that make you question your own ethics, and you'll be like, is this what I'm endorsing? For example, there's the military, and in the military industry you can do a lot of things that are challenging your own core beliefs. So yes, I feel like in any field, and in mechanical engineering where a lot of what we do has big impact, positive or negative, I think this is a valid concern, and I think most engineers have to think about that, and if they aren't, they should, because ethics are important. Was classical engineering worth it? For me, classical engineering, and I understand classical engineering as like the basis of machines and everything, was both interesting and worth it, because a lot of the best mechanisms I design are direct quote-unquote copies of classical engineering and classical mechanism design that no one ever remembered. Oh, this is actually good on a robot. This technology that has been around for 2000 years, this mechanism actually kind of slaps on a robot. So of course, a lot of the classical stuff I studied was very valuable for me in particular. Second part of the question. I have played with the idea of pursuing a PhD during this intermediate period, but I don't know what if the idea of mine is worth the pursuit. A good PhD, what distinguishes a PhD? Wait. Things froze for a little bit. What is... Wait. Am I frozen again? Okay. What distinguishes a PhD from a master's? I hope the stream is okay. Is that in a PhD, you require innovation, especially scientific innovation. Usually in a master's, you can just be doing something like, I don't know, something that is useful. Like, no one has ever tested, I have 20 metals here, no one has ever tested their properties. I'm going to test the properties of these 20 metals. That's good for a master's. For a PhD, you need some more scientific innovation. Why are you testing these metals? Is there some application? Are you developing something new? Are you testing these metals for this purpose? Are you developing... How are you contributing to science with this? That's the main difference. And the best way for me to... There's a lot of ways you can know if it's a good or a bad idea. The best idea would be to find people in academia that are from that field and talk to them. Sometimes you have fear of, oh, I have this brilliant idea and I don't want to reveal my secret idea. That's a huge minority of PhDs, most of them. The idea itself, it's not like you don't have a game-changing idea. You have an idea that is novel and you have the drive to pursue it. That's the main thing. And usually in a lot of PhD programs, you have 1 year just to decide your idea. In a lot of projects, you have 1 year to decide your project. That's how big your project is on the PhD. You have 1 year to structure what your proposal is, to structure exactly what you will tackle. I would say that usually specific is better. Going for, I'm going to develop, let me think. I'm going to make a new car. Okay, there's already so many cars. Like, what? You're going to I mean, my thesis was developing a new robot, but there were nuances into it. But if you're more like, okay, I want to I've studied this physical property. of this fluid, and I want to develop a car engine that works better with this particular fluid for lubrication. That's extremely specific, and that's a good PhD topic. A good PhD topic is like, I've seen a lot of people pouring, like working with bricks, and I think there's the mortar. I think maybe there's a better way that we can spread mortar, and I want to make tests in different mortar layouts and brick layouts and see how they affect. Good PhD thesis. If you look at something that's very niche, usually it's good. Broader things, I mean, you can make a good broad thesis. My thesis was developing an entire robot. My thesis was extremely broad. I failed in this own criteria and I paid the price for it. Even though my thesis was great and I had the maximum marks, I paid the price for how broad my project was. Specificness is good. Niche things are good. Things like even the sole of a shoe. Optimizing the sole of a shoe. Shoelaces. Optimizing the way like shoelaces go through the holes. That's the kind of work. Can it be too specific? I honestly struggle. I think it probably can, but too specific would be very... I think too specific is way more specific than what we think of when we think of specific problems. Scope creep is real, exactly. And that's a problem I had because of my scope. My scope was huge. Is that when, like, I was working on this slice of the pizza, when this started becoming good, when I was starting, oh, now I'm starting to make a difference. Now I'm getting to the juice part. Okay, I had 6 months for this task, need to get on to the next one. And this task is unrelated to that one, so now my knowledge is like, getting focused is good. The problem is, yes, if too specific, if your thesis hinges too much on a specific thing, for example, this must work for my thesis to have value. That's not good. It's better to be like, for example, if the problem is specific, like the holes in the shoes, you can be like, I'm going to test 10 different ways and compare them and see the efficiency, see the materials, change variables, and see the 360 no-scope PhD no-scope max grade. Exactly. And that's the thing. If a topic is very particular, you can approach it in many ways. Of course, I'm going at this with more of an engineering mindset, because if you're doing a thesis in history, maybe, for example, in history, you may choose to focus on the life of just one guy, and that guy seems very interesting, and then you start studying the life of that guy and you run out of documentation, and maybe it's like, okay, I have to increase the scope. But you can do changes. You can do like, I had to increase the scope, so now it's not only that guy, but also his cousin. His cousin is now also part of the thesis. And it depends. Another important thing is, how will you do the PhD? Is this a scholarship? Is this a PhD while work? Because, for example, if it's a scholarship, I did mine in a scholarship. That's why I got locked into something bad, because I had to defend my proposal for the scholarship. And then it's like, okay, we grant you money for this, and now you can't change. I could change technically, but it would be so much work. They beat you through work, and it's like you're locked into it. If you're doing, for example, a PhD while working in your area, and you're thinking, okay, this is a side project for 6-7 years, then you can be more versatile and adaptable, because you don't have a proposal for a scholarship, and you can be... So not all PhDs are the same. You will have a supervisor, and aligning yourself with your supervisor will probably be the main thing. finding a supervisor that is good for your field, and your intentions must align with the intentions of your supervisor. When creating automation and robotic machines, what ISO standards qualifications would you concern yourself? I found some of this work trivial, but I feel like I like heavily in the what standards and QA is associated with. Have you experienced my experience in robotics? Sadly, I'm not the best person to answer that, because I did a lot of lab work. I did a lot of prototyping work. And the main thing about a prototype, what distinguishes a prototype from a finished product, is exactly what you are saying. Is that a prototype, you don't care about standards. I mean, you care about some. You don't care about qualifications. You do not care about safety things. You care about testing. You care about things working. The next step is exactly what you just said, and sometimes you need to have that in mind in the prototype, because you are developing something, then the standards come into play, and it's like, oh no, what I developed is impossible to match the standards. So what you are saying, what you are asking is probably my same question for if I continued in my project, because my robot did not become a finished product, it's still being developed by other researchers. That would be my next question. That would be my next step. My answer to that question is I haven't arrived it yet, so I can't tell you specifically. I know that, for example, one thing that matters a lot is if it's going to have human interaction or not. If it's going to interact with humans, mine was going to interact with elderly people. Safety concerns are paramount. In electronics, for example, you can't have it so that if there's a fail of a signal, the robot keeps going forward. It can trample over someone. It's extremely dangerous. You need to think, what if this system fail? What if that system fail? What if this? What happens when it runs out of batteries? And things like that. Another thing for the topic, before moving on, finding someone in academia helps. Finding the top people at the field and contacting them directly if needed would be a good idea. For example, if it's in robot design, find the biggest robot experts and send them an email talking about your topic. Like I said, if it's $1 million idea, if you feel like you're a genius with $1 million idea, that's different. That's usually not the kind of ideas you have in academia. That's more of an entrepreneurship thing. Plagiarism of ideas can happen in academia, but in a lot of projects, that's not the main thing. It's more about the execution than the idea itself. So you can, depending on, and you can also hide some information if you think it's sensible, if you think it's sensitive information, but you can just contact people. And the thing about the what idea is worth pursuing, don't be megalomanous. Don't see yourself as, okay, I'm a genius that will save the world. The fact that you say the previous career collides with your beliefs and values, I believe you're someone with standards. But don't think like, okay, I'm going to, with my PhD thesis, I'm going to end world hunger. You can do something very meaningful. You can do something very important with your PhD thesis. And sometimes you're not doing it alone. Sometimes you're doing the first domino in an effect that will become very meaningful. But do not try to carry the weight of your world, of the world, right from the get-go, because PhDs are hard. And if you are too megalomanous, a lot of people who struggle also with imposter syndrome or self-confidence issues also have this problem. They feel like, okay, this is too much simple of a topic. I'm not that good. I need to make my topic harder. And you are sabotaging yourself by doing so. So I believe most ideas would be worth pursuing, and sharing the idea, having feedback, is one of the best ways to confirm that. How did you commit to what you studied in your postgrad? What frame of mind, what questions did you ask yourself that gave you the confidence to pursue it? Mine was particularly simple because I did my master's thesis, and my master's thesis was starting my robot. The development of my robot. And then my PhD thesis was like, I'm enjoying working on this robot. I will do more of it. I will continue. My PhD was the continuation of my master's, which is an exception. There are more people who do this, but it is an exception, and it made it easier. It had a sense of continuity, so I think by doing so, I dodged a lot of questions that can plague the minds of a lot of people. I was lucky there. But yeah, for example, my robot is made to help people. I talked about this in the last stream. It's made to help the elderly, but depending on how the technology is used, it can bring bad consequences. If the technology is misused, that's something that's normal. Technology is technology. For example, I do believe a lot of generative AI thing in an alternate timeline, in an alternate scenario, they could have been doing a lot better. But right now, they are doing a lot of harm to society. There's a lot of bad agents out there. And sometimes people who are developing the technology know. Sometimes people are just chasing the profits and things. Other times people can be good, can have the best intentions and develop bad applications and things like that. But I think the most important question you can ask yourself, number one most important question, number one, I'm going to write it down. This is the number one question you have to ask yourself before starting a PhD. Do I want to do it? That will be the most important question. Do you want to do it? If you don't want to do it, you can do it, but it's going to be much harder. Motivation and perseverance are the most important things in a PhD. It's not like in the movies where it's big brain, million equations. A lot of the hardest part of the PhD is surviving through the slog. It's surviving through the hurdle. It's going through the mud of the PhD trenches. And if you want to do it, that part will be a lot easier. And do I want to do it in a term of, do I want the PhD? And do I want the project? These are the two things. Do I want the PhD to, for example, for self-value, self-worth, because I want to research? And then is the project something I want to work on? Do I believe in this? You will question this question along the way. You may love your project at start. Let me tell you, 2 to 3 years after you start your PhD, you will not want to do it. There are a few exceptions, but I've met amazing people with amazing projects that did amazing work, and even they, after 3 years, were like, why did I pick this? This is so bad. It is normal. We follow trends as a what did I just click? I hope I'm still okay. We follow trends as humans, and it is very normal for you to reach at the point where you're just so saturated of your work, and you start getting, since it's so much time, the what ifs are such a plague. Even if your project is like a 9 out of 10, you will be plagued with what ifs, and it's like, if I did this, if I did that, and you will grow along the PhD. You will grow, regardless of what your PhD is. Even if you're like, oh, I'm 70 years old, I'm at the end of career, I'm doing my first PhD, will I still grow? Yes. It is a journey that even if you give up on your PhD, you will grow from the experience you had along the way, and your vision will shift a lot, and probably the vision that you had when you started will not be the same. But I think for starting, this is the number one question that will make you decide if you want to commit or not. Do you want to do it? Do not think, I mean, you can think there are things like, okay, I will have a better job, the market and thing. That's what comes after. To reach the after, you have this, to survive the during. And to survive the during, this is the question. Do you want a PhD? If you want a PhD, go for it. If you don't want a PhD, or you're not sure, I think most people are not sure, think about it, weigh the pros and cons, see what are the consequences of failure. For example, I have a job and a PhD will be a side thing. I can quit anytime. Consequence of failure is almost zero. Okay, go for it. I have a scholarship, and if I fail, I will have to refund my entire scholarship. Maybe consequence of failure then it's quite big. So make a decision, think about pros and cons. But the main frame of mind I would say is, do you want to do it? And if you want to do it, write down why. And on the days that you are down, because there will be downs on a PhD, remember yourself of that. And another thing is that write them down, don't decide on that day, wait a week without looking at what you wrote down. A week pass, you look at the things, do you still relate with them? If you do not relate with them, maybe, okay, these emotions are too premature to join a PhD. If after a week your vision is still aligned, maybe it's like, okay, maybe there's something going on here. Maybe we are cementing something. I took quite a lot of time because this is not an easy question. At the end of the day, before going to the next question, the main thing I can tell you is that I am not qualified to decide if you should do a PhD or not. I can give you some tips like this, but at the end of the day, you are the only person who can decide that. That's my number one tip. You are the only one. Only you can find a way, Mr. Anonymous. I believe in you. The fact that you are anonymous makes this cooler. Zumu, my mod, Mr. Zumu. Oh, a cool question. A cool question. This question, I was browsing through the questions, and most of them, I mean, almost all of them, when I saw them, I was like, I like this question. Yeah, it's you again, Mr. Zumu. When it comes to physical tools, what are your favorites most used? Are there tools that you love but barely use, or maybe tools that you use a lot but really dislike using? Okay, I'm going to go through some tools at a time. First, I will start with a tool that I love and hate the most, which is, okay, how do I design this? Maybe like this, some clamps over here. Counterpoints supporting on this end. This can be on a trolley, and then you have a thingy going here. Have the machine head, you have this that goes this. A lathe. I'm basically designing a lathe. Lathe is probably one of my most loved and hated machines. Love it because sometimes we are irrational creatures and we have to go for things we like. I think working on a lathe is beautiful. I think it is so beautiful to see the metal, like the metal barbs forming like, and the revolution parts, the metal gets so shiny. I think lathes are beautiful, and revolution joints are a staple. Like then you have a bearing, you get this into the bearing, are a staple in engineering. Revolution joints in robotics, and a lot of what I did was related to lathes. Like you have a motor, and you have the axle, like something like this. Oh, this is more of the motor itself, and then you have you machine an axle that fits into and goes into the wheel and things like that. There's so many important parts that are Revolut parts, and they were all made in a lathe. For those of you who don't know what a lathe is, basically in a drill or in a milling machine, you have the tool rotating and the part is immobilized. A lathe is different because the part is rotating and your tool is immobilized. I mean, the tool can move back and forth, but the tool is not rotating, it's the part. That's what, basically, that's the defining feature of a lathe. Why do I also hate lathes? First, and this is not generalizable, the lathe I was using had gaps, so this knob, I could move it around like 2 degrees, and this is like, you're working with hundreds of millimeters. I would move it like back and forward, and the machine was not moving. I needed to remember that, okay, I took this measure at like the rightmost position, and then keep going for that position. I need to mind the gaps of the machine. I was working in a really bad lathe. The metal that I was using, I used good metal and also bad metal. Machining bad steel is horrible, by the way. Using construction steel for something that's not the point is horrible. And the other thing is that for millimetrical things, since the machine doesn't have a lot of precision, I had to hand sand the parts. What does that mean? It means that you have here a big chunk of steel, and you have your part here, and this big chunk of steel is rotating fast. You feel the wind rotating from it. And you have, I'm hand sanding, so I have some sandpaper, and I have a finger here and a finger here, and I need to get close to this. And that was so scary. Sometimes it pulled a little bit, and the instructor was like, oh, hold it lightly, so if it pulls the sandpaper, you let it go. Do not let yourself be taken by the machine. And I'm like, this is so dangerous. So I love lathes. I think they're one of the most beautiful machines. But the fact that I was working with a bad lathe and the finger losing potential is crazy. Also, long hair in this type of machine, in most machines are, but in a lathe, long hair like a ponytail or long beards, I no longer have, but I used to have long beards, are so dangerous here. There's so many danger aspects in a lathe. There's also wear your goggles. Working in a lathe, I have quite a lot. Oh, let me draw my eyes. Sexy anime eyes. Working in the lathe. Yeah, this is me. Let me grab my... Why is this turning out so good? Why is my self-portrait turning out so good? Yeah, use your protection goggles. Because sometimes these metal sparks will fly, and it's not just metal hitting your eyes. Sometimes the part started smoking, you would apply oil, but this could be incandescent, very warm metal flakes coming off. And I had one. I've talked about this story before. I've had a flake of metal, very hot metal, falling into my shirt. And I was like, ah! And I've had specks of metal at the same temperature hitting my eyes. And I'm like, yeah, I'm glad I'm wearing goggles, because I know people who have permanent injuries because of this. Well, let me just address ZP Piglin, and then I will continue the tools question. Greetings, this may not be directly related to mechanical engineering, but it's chemical engineering. Really well played, future-proof and stable side of study. If I need to choose after I finish school. Oh, is chemical engineering really well paid, future-proof and stable? Okay, my main answer to that is that it depends on too many things. Because, for example, when I started studying in university, civil engineering was one of the worst areas. Employability, almost zero. And nowadays, it's good. The markets are so volatile. I don't... Future-proof, I honestly think there's no area is future-proof. if I'm honest. I shouldn't be laughing. Freshly finished chemical engineering PhD here. Ask me about my unemployment benefits. Yeah, I have a field, for example, physics, there's physics engineering as a field. And I have a feeling some of those fields you can only survive in academia, or if you're like, there's like a good job for the top 0.01%, or sometimes even the top 0.01%. And a lot of people, and this stop, maybe sometimes it's because you have good influences or you had the right supervisor. I feel like those areas sometimes that are more theoretical adjacent, and that they don't have a good niche defined. For example, mechanical engineers have so many areas of application, and that helps a lot. But yeah, continuing on the tools question, and thank you Math Magician for providing your support in answering as well. But I would say, of course, don't base your answer just because, okay, I saw a guy on YouTube saying, commenting that he's unemployed. Try to get more information about how things are in your area. For example, maybe you live in a place where there's a lot of textile industry, and that can require chemistry, or there's a lot of... Maybe you live in an area where there's a lot of demand, or maybe you live next to an area where there's a lot of demand and you're willing to migrate. Are you willing to migrate or not? That also should be a part of your question, because some engineerings require you to leave the country more than others. So I talked about the lathe, and lathe is a love-hate relationship. Drilling machine is probably my favorite machine. Not that dangerous. You want to make hole, machine make hole. Easy, simple. I love myself a good drilling machine. Like the thing you push down. So drilling machine is great. Okay. Tool now that I absolutely hate is using a bandsaw. And another is, I think the English name is chop saw, which is basically a huge ass. That's the technical term, huge ass. A saw. Okay, let me. Right. Okay, I can't draw a saw. Wait, a huge saw that you use to cut, for example, a metal pipe. And it has like lubricant going here. This is, when I say huge, this is like maybe 40 centimeters. Let me just read Sumu's comment. The market changes a lot. I think good advice is to choose something that is good feel in terms of employment, but also something that you don't hate, because otherwise you might... Yeah, it's... choosing your area of study is one of the hardest decisions, and none of us have enough maturity to decide when the time comes. And some people make a really misinformed decision and they hit the jackpot, they end up loving it, and others do all the research and then they get disappointed. An advice I would give you is, a lot of people have shame in changing fields. Go into the field that you want, but if you're not enjoying it, do not feel peer pressure to stay. If you feel like you should leave, and you can, not everyone can, if you feel like you should leave, do it. That's another tip I would give. Okay. This saw I hated because our saw in our workshop was missing one of the teeth, and I don't like loud noises. I'm not a fan of a lot of noise. This thing cutting bars of metal, it was so loud. I hated, and I had to use this quite a lot. I hated the freaking bad, and the cuts. I mean, this is not supposed to make perfect cuts, but they were so bad. It's like have this pipe, and the cut was, instead of being like flat, you'll get like an angle here and another angle there because it was eating so much of the material. That's supposed to happen, but I hated this piece of machine. And then it was pung, 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 because of the missing teeth. It was horrible. And the bandsaw, this was dangerous, but not that much. The bandsaw, because of how dangerous it is. Because the bandsaw, I think that's the name, a bandsaw, is basically you have a saw that is going like a belt saw, and you have the piece that you are cutting, like a wood piece, and you're moving it towards the saw. And usually when your fingers start getting close to the saw, you'd get like another one piece and push this one piece because you don't want your fingers close to this. Because this is a very dangerous tool. And because I've seen people not lose fingers, but have nasty finger injuries. I've heard about injuries in other tools. In the bandsaw, I've seen injuries. So for me, if what makes me hate a machine is lack of safety, I wish doing all mechanical engineering work. Like, have you seen a blacksmith? Blacksmithing is the coolest thing I've ever seen. As a kid, my dream was to be a blacksmith. But now I know how dangerous it is. I wish all of these machines were only cool, but they are scary, and you should be scared. Nothing scares me most than seeing someone, like a student, walk into a metal workshop without fear. That scares me. Lack of fear scares me. Fear shouldn't immobilize you, but fear teaches you to respect and be prudent. And I see a lot of people who lack self-confidence, and because they lack self-confidence, they want to project an image of, oh, I'm not going to ask any questions. Oh, they don't want to project any weakness at all. But this is a place where you should project weakness if you have it. And I've seen it happen. They walk into the workshop, they don't know what they are doing, they don't want to say that they don't know what they are doing, and then injuries happen. I've seen injuries happen with zero fault of the person, but if I had to say it, I would say that I've seen like 5 or 6 accidents. One of them, the person was absolutely innocent. Machine failure, other people didn't follow regulations, things were poorly set up, zero blame on the user. The other 5 were 100% user fault. So be careful. Be careful. And yeah, the main thing that makes me hate a tool is it being dangerous. One thing that I loved working was with the CNC machines, like using G code and program, but that would fall into the part of I like using, but I didn't use enough because it is cool. You see the automation, you see you set up the code, and then you have they are safe. Most of them are extremely safe CNC machines. You're not putting your hands there, they are closed while they are working. These are not well advanced machines or something. I love the welding iron of electronics components. I've even used it sometimes to mold plastic, but that's another one. I didn't damage a good iron to mold plastic, but I love welding irons from electronics to do some small circuitry, to connect some connectors, melting the melty stuff. I don't know the English name. So this one is a big thumbs up for me. And this, yeah, you can get injured here, but it's not like a life-crippling injury. That can happen, but a lot of the injuries here... A solder, exactly, a soldering iron. Most of your injuries in the soldering iron will be like, ah, fuck! And that's your injury, and it hurts, but it's not bad. I would rather have an injury that hurts a lot, but doesn't last a lot, than an injury that doesn't hurt that much, but stays with me for life. So soldering iron, solder iron would be one tool that I like. I also like, I'm going to call this a tool. Now I like it. I used to hate 3D printing because you worked with really bad 3D printers. Now I really like 3D printing. 3D printing probably one of my top things to use. Oh, and my number one tool. The robot I designed for my PhD thesis has around 1,400 nuts and bolts. So what's my favorite tool of all time? Like, without a shadow of a doubt, it's the freaking electric screwdriver / drill that you can have here. The bit. This is by far my favorite tool. It's the one I use the most. It is the one that I would probably have like some horrible tendonitis or something if not for this. I was so tired. My lab had one. I bought one for myself because I needed it that much. I needed to fasten so many screws even to assemble furniture from IKEA at home and everything. A freaking electric screwdriver. Yes, electric screwdriver is the best tool ever made. I know it's not. I left it for last, and I do understand some people may not qualify it as like, oh, it's not an actual. Nah, this is my goat, my best tool of all time. And then usually at the end it can have like a drill symbol because you can use it as a drill as well. This is my best tool ever. No doubt about it. Like I never did welding, but I mean, people losing eyesight and things scares me. Oh, I have more notes. One that I never used, and it's surprising that I never use it. It's a coincidence. I've never used a Dremel. I think that's the name. That you have a thing like this, and then you have a rotatey here, and the rotatey can be like a saw, can be like something for sanding. I never used a Dremel, and I know that electronics people use them a lot. Cosplayers use them quite a bit. I never used a Dremel. They sound cool. I also like I never did sandblasting. No, I've used like electric sanders, like more of the round type, like those sanders that you just have a disc and it is rotating and you're like for woodworking. And now I've talked about some, but yeah, I never did sandblasting. Seems cool. I'm going to talk about the two tools that I hate the most. Some honorable hate mentions have been done. Yeah, I'm also surprised myself that I never used a Dremel. I'm surprised with that fact, but it is true. My top two hated tools, and based on my speech so far, you can probably maybe guess. Number two, my second most hated tool would be, can I draw this? I think the English name is an angle grinder. The freaking angle grinder. It's such a dangerous tool. So many things can go wrong in an. I never used an angle grinder, and this I can say the reason why I never used an angle grinder is purely because of fear. 100% only because I've seen so many things go wrong with an angle grinder. I had someone who knew how to use one well, and whenever I need it, it is a super useful tool, one of the most useful tools it existed. Whenever I needed, I was like, okay, can you please use your angle grinder to do this? And he was like, yeah, okay, very kind person, not saying in this tone, but angle grinder is definitely one of them. This is my second most hated tool. The first one, this is also one that's more for other specific uses, not as much as a metal workshop. Oh, another I liked, I forgot. This is not a hated tool. The tiku-tiku. That saw for woodworking. I love the tiku-tiku. Okay, another like tool I just forgot. It is like that saw that you have for woodworking that's handheld. And it's just a saw that goes up and down. And you have like a thing you press brr, brr, and it goes up and down, and it's for you're cutting like a curve or something, a freehand cut on a piece of wood. I like using this one. Need to be careful not to get the saw stuck and things like that. I have a Makita angle grinder. It's a scary tool. Yeah. So this is one I like. My number one most hated tool. I do like the anime, but I hate the tool. Yeah, tiku-tiku, somehow my experiences with tiku-tikus were very good. But yes, me saying that I don't like saws, this is my number one. I never used one of these in my life, and I probably never will. Only if I'm forced to buy a chainsaw. It's such a dangerous piece of equipment. It's so, like, I was talking about it's one thing to know that things happen. It's another thing to see them. I know cases, I think saying what happened is too bad for YouTube or Twitch as a platform. I know cases where working with chainsaws had the worst possible outcome. Chainsaw time is a good time. Chainsaws scare me. I understand the if you know how to use it, and it must be such a feeling of power. It must be so empowering to wield a chainsaw. And I like the anime Chainsaw Man. But I know so many bad stories about chainsaws, how they can get stuck and then they kick back and things like that. Nowadays, a lot of them have more safety features, and it's harder. If you're doing them right, it's harder for things to go wrong. But still, I respect chainsaws as an important tool. I will never pick up a chainsaw. These things scare me. I'm human. I'm a VTuber, but I'm also human. I'm allowed to have fear. Angle grinders and chainsaws are where I draw the line. I don't mind using a lathe and having my hands close to the rotating parts. Yeah, chainsaws are especially scary since they kind of shred instead of actually cutting. Yeah, exactly. And there's so many levels at which they can go wrong, and yeah. Chainsaws are my #1 most hated tool. Now, let's see. Fear of a tool is the start of respecting a tool. True, and I have talked about how fear is important. Okay, next, I have a funny one. I have 3 more questions to go. I think I stopped accepting submissions on the form, and I think I did a good call, because I think the timing of the stream will be perfect for my own plans. I also had a long day today, was celebrating the birthday of my good VTuber friend Amaru Aranue, was on her channel. It was really fun. She sent me coffee from Bolivia. I have such cool friends. Thank you. And I have friends in chat as well, so if you are my friend, shout out to you. I pick good friends. Bread and toast. Why is Excel the best and most powerful programming language? Excel is a beast. Excel is an art form. Excel is a thing of beauty. For those of you who don't know, in my master's thesis, I developed a new mechanism. A novel mechanism. It had some, it's so unique that I can't draw it because I will be doxing myself. I drew a very cool new mechanism. Is it the best mechanism in the world? No. But it is very unique. It is very cool. But I can't talk about it that much. And let me draw something that doesn't resemble my mechanism at all. Like a bar like this. Okay, I'm going to do a 5-bar mechanism with maybe a spring here connecting to here, and then there's another bar here. I'm just drawing a random mechanism. This could be a mechanism. Like you do boing boing and it does boing boing. That's this mechanism. And if I change a value here, it will affect that and yada yada. There's a lot of interdependent variables. And when you're working, for example, I was working with steel pipes. They can break for a number of reasons. They can break because, let's draw it from this view, because you are bending them. They can break because you are tensioning them or compressing them. In steel, the equations are the same. They are not the same if you're working with concrete. Concrete resists compression but not extension. For steel, it is the same. You can do what's called torsion, which is like torsion, or you can do shear forces, which is like you have a force here and a force here, and that's causing shear of the metal. And you don't have one of these at the same time. All of these four types of forces, types of strains, are working together, and they are provoking 2 types of stresses. You have your tension stresses and your shear stresses. Like these 2 cause more shear stresses, these 2 cause more axial stresses, the bending, but you have these two. And depending on these stresses, this is what's causing damage to the structure. You'll have to determine a certain profile of aluminum. And at the same time, this has holes, which are causing what is known as stress concentrations. And these factors will change. And maybe, for example, you're changing the stress concentration factor because you have like a rod here to create this revolute joint. And this rod also has flexion, also has tension, also has shear, also has all of these. So if I'm like, oh, this rod is too weak, let me increase the diameter of this by 1 millimeter. Now this hole is bigger, even though it's filled, it affects the structural integrity of this steel, and this is all a loop. How did I solve this? Is this some sort of claw? Could be. Basically, this is described by equations. I took all of these equations and I wrote it in Excel along a bunch of sheets, defining these were like 18 bodies. Each body had like 6 components, and all of these 6 components have 4 types of stresses provoking 4 types of strains provoking 2 types of stresses. And I had basically a thing with my input variables and a sheet with my stresses and strains. Not even the stresses and strains, I had my safety coefficient. My inputs would also include the material, and this will have like all 18 bodies, and I would be like, okay, if I use 8 millimeters for this will be like, okay, safety factor here is 2, 3, because I have an internal safety factor, like this factor just needs to be 1.5, and here 1.2. Okay, let's increase this, let's change this material. And I was playing and trying to find the ideal values. I even had a color code, and once this would all turn into mild green, which is all above 1.5 but close to it, because if n equals like 20, this means that the part is 20 times stronger than it needs to be. And that's waste of material. If n equals 0.8, this means that the part has 80% of the strength I need, so it will break. It's not breaking, you're dimensioning things for bending, because usually when not bending, deformation, it will deform, and deformation will lead to breakage. You do not size things for breaking, you size them for deformation. This is plastic deformation, this is permanent deformation. You don't want that to happen, so I have an N of 1.5, and I had all of this, and this was all just Excel. And if you read my Python description of what I did, that's basically what I had. It is equations and it is Excel. The only reason why I had to upgrade to Python was the fact that I had the simulation over time. If I didn't have simulation over time, I could use like machine learning, all of that. I could use all of that in just Excel. The only reason why I needed to upgrade to Python was because Delta T. But I believe there's a lot of people don't understand how good Excel is at solving equations. A lot of equations, a lot of physics can be directly translated into equations. You implement them into Excel, and then you have such an efficient program with good... I mean, Excels can start... If you start having like 30 to 40 million cells filled, I've had that happen, it can start lagging. If you have 40 million cells and some 50, 60 graphs in the same page, Excel will complain. But before that, it's still a viable tool. And there's a lot of things. Like, you can do ifs. You can do ifs in Excel. I didn't even have that. My Excels, I have really... Even using Python, I still... Oh, light just flickered. I hope... There's thunder outside. I hope the stream survives. Only 2 more questions. I don't know if you could hear the thunder, but that was a loud one. and every light just flickered. But yes, I used a lot of Excel. Let me just read that felony saying. And I think Excel... Question, I assume you heard about Wolfram Alpha in XQCD and assumed it was used a lot in engineering, but haven't heard you mention it. Is it a tool you've used or used? I've never used Wolfram Alpha. I've never used Wolfram Alpha. And none of my professors... It could be a specific college thing. I'm searching for it. When is this from? Okay, 2009, so it's not... I actually never... Yeah, I've never stumbled upon it. So yeah, that's my honest answer. Actually, none of my professors, if they talked about it, I didn't register it. An World Excel champion has a really cool use case of what a spreadsheet can do. True, it is really cool. One day, okay, future idea for engineering streams. I have other engineering streams for it. I'm going to probe your interest right now on one of these. Would you be interested in... Okay, I have two from today's stream alone. Let me go for a different place on the sheet, which is the... We talked about my code, so code hell. And also, this can be the same stream. Spreadsheet heaven. Because spreadsheets are nice. But this will be one stream. I wonder if people will be interested in machine design. What I mean by machine design is doing exactly what I did for my work for the most part, which is I create a problem on stream that I want to solve. I draw the machine, I order the parts, I build the machine, literally, physical prototype, I test it, and I make it work. With motors and everything. I wonder if people would be interested in that type of content. In me, starting from CAD design, all the way to prototype. Some parts, for example, if I have to cut some prototype, we can go for prototype. Code hell, spreadsheet heaven, yes. And 3D printing. Some parts, for example, the 3D printing, I won't do it like we are all looking at the 3D print. Like, probably I'll do off stream, record a video, and then during the stream, like, compared to previous stream, we had the parts ready. Here are the parts. Let me show you a time lapse of them printing, and you would follow along the process from conceptual design to finished product. I wonder if people... I see that Sumo is interested. I am probing that idea. If, like, raw mechanical design, like showing literally what mechanism design is and how we tackle the problem, from boring equations to... It would be fun and interesting. Nice. Glad to have your feedback. Thunder is so bad. But yes, Excel is really good and it solved a lot of my problems. Especially, yeah, 3D printing would be a main part of it because I worked a lot with a lathe. Right now, I'm not working at the university. I don't have access to a lathe, for example. I would have to condition the design with the tools I have at hand. I have a 3D printer. 3D printing would be a part of it. I don't have a lathe. Lathing wouldn't be a part of it because I don't want to pay. Lathing services can be quite expensive, and I also don't want to be like, hey, can I use your lathe, please? So probably one of the restraints would be I would build a machine with just tools that I can use and I wouldn't have to sacrifice fingers. Okay, 2 more questions before the storm takes me. Pickle mechanic! When it comes to setting angle for a tool bit, is this correct? The angle of the dangle is inversely proportional to the heat of the meat, provided that the maxes of the axis and the gravity of the cavity remain constant. I don't know this one. I'm usually good at meme knowledge, but this definitely sounds like meme knowledge from somewhere. I will say that setting the angle for a tool bit is very complex. For example, if you are drilling holes, drills have an angle, but it's usually, I think it's either 120 degrees, or what was the other one? There are 2 popular angles, so you're not thinking about these angles. A lot of them are just normalized. But for example, if you're working in a lathe, you have the part here, and you have your bit that's being held by an iron, and you can rotate this. You are defining your angle of attack to the piece, and this is a very complex topic. It depends on the material you are machining, depends on the speeds you are working. For example, one thing that's counterintuitive, if you're eating a lot of material and doing some rough passages, you want to penetrate a lot and remove a lot of things, and the part needs to move slowly. If you're doing like, okay, just removing the surface and I want it to be mirror finish, you want the part to move very fast. There's a lot of machining parameters. Even this angle, this tool has it has angle in this plane, but if you look at the tool from the side, it's like this, or it could be like more like this. That's the same trapezoid front, and you can also adjust this angle here. And you want basically one good way to check the angle for the tool bit. I like how it doesn't matter how silly the question is, I will always answer with the engineering knowledge. When you're working, I'm using the lathe because the lathe is one of the main things where you have control over all the angles. A lot of them are defined by the tools you are using. In a lathe, you are controlling a load of work parameters. And when you are, it's like sharpening a pencil. When you sharpen a pencil, you have an apara a formar. You have the shavings forming. This sounds really complex. I can tell you, Zumu, that I studied this. I had good grades. I forgot everything. Only after spending 6 months working the metal myself did things start to get intuitive. I learned all the theory, and it was so counterintuitive that then I forgot. I only learned it through cementing it through practice, and then it starts making sense. Then you start adjusting things and you feel them in your hands, and that starts converting itself into memory. But one test you can do is that if the apara that is forming is like bits are flying, the angle is wrong in one way, and if the apara is starting to form a coil, and this coil never breaks, like it keeps going, it's also wrong. What you want is that this approaches, it starts forming a coil, then it breaks, forms another coil, then it breaks, forms another coil. If this is removing material like this, forming coils, and they are breaking, probably you have all the right parameters for the material you are working. You have the correct penetration, you have the correct velocities, you have the correct angles. This is the profile that you want. A lot of machining angles, this is how you adjust them in the lathe. You look at how the shavings are coming off, and you want this profile of shavings. These look cool. I have one of them in my drawer. I can share maybe where in which drawer is it? I have like, it's my first time machining, and I have a really cool long shaving. I want to save it. I have one of these. I can share later on my Discord or on X or something. But this is the profile that you want. Always breaking, because if this is always breaking, what you'll have is like in a microscopic level, and that causes instability. If you have this long, it can start wrapping around the piece and then going back, and so you don't want you want the things going off like that, smooth and steady. That's the that's the breaking profile. So yes. Oh no, not yes. So yeah, when it comes to setting the tool bit, that is the angle of the angle is very proportional to the heat of the meat, provided that the max heat is another thing. In some metals that I've worked with, you needed to constantly add lubricant, and lubricant, people think, okay, it's for things to slide. It's to lubricate, but it's also to reduce temperature. Oil cools down parts, and a lot of times, like in a lot of saws, you have literally a jet of lubricant firing 24/7. That's how important cooling is, and if parts start dilating because of heat, then all of your dimensions will be wrong. Also, TheNando also has a PhD in goofy noises. True, that's the VTuber side. And now I'm going to go for the final question that I have. And that is... The person is probably thinking, did I skip my question or is it the last one? Sugi Yamagawa, you're the last question. And this is a fun one. This is a really cool one. Do I have blank space? I have blank space here. Oh, I could have asked my own question, but no. Of the 6 classical simple machines, which are the following: lever, wheel and axle, pulley, inclined plane, wedge, and screw. Which is your favorite and why? And I will give context to those of you who do not understand this question. Let me just... This was basically in the Renaissance. The intellectuals, like in the Renaissance, there's a lot of machine design. You have Leonardo da Vinci, you have everything. You have the revival of the Greek classic philosophy and everything. The rebirth, some would call it a Renaissance. And they define like 6 simple mechanisms that are the basis to multiply force or to increase your efficiency. And they are the lever, which people know from Archimedes: give me a lever long enough and I can lift up the sun because of torques and things like that. There's the wheel and axle, which you often see in old wells. It is like when you see this and you see a thing here and the rope picking up a bucket. You have the pulley system that a lot of us have studied in school and everything, that multiplies the forces and things like that. It's very important in historical construction and things like that. It decreases, depending on the diameters of the pulleys, it can multiply forces. Once again, a lot of these mechanisms comes down to torques. You have the inclined plane, which is the simplest one to explain. You have an inclined plane and that makes it easier for you to push something up. A ramp. You have the wedge, which is basically a way for you to... one of the main applications is, for example, if you have a piece of wood. Let's grab like a board. No, let's... Not a board, but it's better with a cube piece of wood and you have a small crack here or something. And you can drive a wedge here and use it to increase. Oh, it's better. It's used a lot in stoneworking, wedges. Like to split stone masons use wedges a lot to break stone and to channel the fracture. And then you have the final one, which is the screw. And the screw is the same screw that we use to fasten nuts, and I'll talk about why. But when we are talking about this screw, it's often the same that we have, for example, in I think it's called a vise, one of those machines where you are closing this, and you have here a screw that you are turning with a lever, and the screw is going through a fixed part, and you turning the lever makes it so that because the screw's threads are moving through a fixed plane, the screw goes forward or backwards. It converts rotation into translational movement. Okay, let me go back to OBS. Can you see all of them? You can, kind of decent. In Hello, when the barman had faked his death, the other characters held a renaissance. Nice. Give me a lever and I will lift up the world. Exactly. Oh, primitive technology device. Yes. Yes, stonemason extraordinaires like an Arnaldo Costa. Exactly. my favorite one of these, for maybe not the reason that you're thinking, is the screw. And my reason for loving the screw is quite simple. All of these are vital. You need all of them. In my work and in my day-to-day life, I use screws quite a lot, and they have a property that I adore. And it's the same reason why screws are used alongside nuts. Screws were originally more for this, for transmitting rotational movement into translation. That by itself is really cool. You're rotating a screw, and that screw is converting into something going back and forward. Transforming rotation into translation is already cool. Like this. For example, if you have a mixer, a hand mixer, you have another type of screw. It's called in Portuguese parafuso sem fim. In English, they call it a worm gear drive. Okay, this is going to look wrong, but bear with me for a bit. What you have inside of an electric mixer is you have a motor here. You have here a worm, a parafuso sem fim, and you have here two gears. And this screw rotating is being transformed into rotation of these two gears in this way, and that's how you have the of the hand mixer, the batedeira. This is what you have inside, and one of the cool things about this mechanism is that each rotation of the screw will advance the gear 1 teeth. So if this has like 60 teeth, the screw is going and this is going very slowly. And that's a lot of electric motors are fast and don't have a lot of force. By using this, you are getting what you want. You want more force and less speed. And this is the type of the multiplication you want. But my main reason for loving screws is what we call self-locking. A self-locking mechanism is incredible. And I'm going to explain what that is. I love self-locking mechanisms in machine design. I have here my lever. And I am lifting the world here. I'm really confident right now. I'm here. I go down, world goes up. I've achieved my task. Now, I leave this, and what happens? Well, the world comes back down again. If I'm not applying force, the system returns to their previous state. And the same for the pulley, for example. I can lift something up. If I don't use a brake or something, you can break them, of course. Brake in topping, not in... I let it go, it falls down. On a screw, I rotate the screw, and it moves something forward. It's moving a clamp forward. Was that a hawk to what? No. And this is pressuring, like I'm squeezing a part here that I want to drill. And this is literally one of the uses for it. I'm squeezing a part that I want to drill. And I used a lot of force here in the lever. And I've tightened it. It's a strong force. And now this is squishing. And the fact that from the moment we have material squished, the material is exerting force. The material is doing force this and this direction. But I let go. Does it go back? No, it stays there. If I have a screw here, for example, and I use that screw to drive this and this goes down, the world goes up, I let it go, the world is applying a force here, and that doesn't make the screw rotate. You rotate the screw and this goes forward, but you pushing this doesn't make the screw go back. That is a self-locking mechanism. Not all screws are self-locking. We have equations for that. It has to do with the thread angle. Like if the thread, for example, is too much like this, it will slide, and you can push this side, and that will unfasten the screws. But screws are self-locking mechanisms. That means that you apply a force, the screw moves, you let go, the screw is stopped. If you have, for example, a hospital bed or a garage door, let's use garage door, because a lot of people have, not garage door, garage gate. One of those gates that, okay, the gate is closed, and you have a cylinder like this, and these are usually electrical cylinders. And you push a button, and like the cylinder should be expanded in this scenario. Let's just draw one of them. You have the cylinder here, you push the button, the cylinder shortens, and that opens the gate. If you try to manually push the gate or not, the cylinder won't budge. Why? Because what we have is literally the end case, the end of the cylinder is working like a thread. Oh, this is more inside. Yes. And you have like a screw going in this thread, and you have the motor. And the motor is rotating this screw. The whole cylinder is moving back and forth with the screw mechanism in a lot of cases. With the screw mechanism that is multiplying our forces. And that also means that if you lose power, you're not applying any power, this still won't budge. You can't push the cylinder and hope it to cause a rotation in the inner mechanism. And that's great. For example, if you have a hospital bed, like a lot of them have this exact cylinder, electrical cylinder. If this was not a self-locking mechanism, you had a power outage, the person would fall and it will not be like, it's good. The person would crash. But this is a self-locking mechanism, which means that even if we lose power, it stays in the same position. And this is great for mobile robotics, because one of the main problems of mobile robots is that they have a limited... Oh, this is on the way. They have a limited energy supply. That's the main difference between a fixed robot and a mobile robot. The fixed robot, you can plug it, and you have limitless, quote-unquote, limitless energy. A mobile robot, since it's moving around, it has batteries. The more batteries you need, the heavier it will be. So the more batteries it will need, so the heavier it will be. So the more batteries it will need, so the heavier it will be. So the more batteries it will need, so the heavier it will be. So you do not want to have a lot of power consumption. If you use linear actuators, you just need to move the arm into position. The arm grabs what you want, and then you have to exert no more force, no more energy consumption on the arm. The arm is there, the position has been achieved, you have a power failure, the arm will not punch you, it will not fall on top of you. You do not need power to lock the position, it is self-locking, it locks by itself, and that's the main reason. I don't think this is the best mechanism for more multiplication, and we are talking about the 6 classical machines. I maybe think pulley is the most elegant for power multiplication. Of course, it will be gears, but pulleys are kind of primitive gears in a way. Gears are my favorite, but for the classical, it would be the pulley for power alone. But since I'm thinking about general applications, and the transforming of rotation into linear motion is huge, because most electrical motors produce rotation, not linear motion, and then it is self-locking. Those two things alone make me love the screw. I love getting screw. I love screw. That sounds... But yes, that is my final question of today. Thank you for those who asked more, and I hope I provided a clear, good answer to all of them. I'm really glad that I like a lot of questions. I like that I could address the degrees of freedom and things like that. For example, in the robot learning from human motion, programming was fun, talking about the machines I designed. But Sugi's and Zerzon's question allowing me to address machines and mechanisms, man, I could go on all day. I will make a part 3, but not for now. I think for now, I would do a break. Maybe a 1-month break. It's not like, break forever. This was bi-weekly, so 2 weeks from now, it's going to be... I don't have anything on my schedule, right? No. It's going to be another engineering stream. I will do an engineering stream always once every 2 weeks. But next engineering stream, like super heavy engineering like today, will not be a Q&A. I want to do other things and probably return to Q&A in the future. I've closed questions for now, and a break forever is not really a breakthrough. I've closed questions for now, but I will do more of these sessions. So if you're interested, write down your questions so you don't forget it, save them, and you will have your chance to pose them. That was it for today. Let me check. Oh, I don't have schedule for next week. Next week it's going to be a little bit more brief. Monday I'll be doing Go, and Friday I'll be doing a collab with Amaru Runway. It's gonna be fun. Well, it's gonna be more of a goofy stream next Friday, not as serious as this one. And Monday just a classic Go. But let me see if there's anyone to raid. I'm like, let me see if there's someone to raid. Is Zerzon or Zumu streaming? No, they are in my chat. Yamakawa is also not streaming, so I'm probably not gonna raid on YouTube. On Twitch, I have more targets. Oh, sorry, I don't know if you heard Hera speaking. Oh, let's raid into Bergwin. He's casting. He's doing Age of Empires stuff. Casting that casting his own cup, his own tournament. So let's raid into Bergwin. Bergwin's great. Bergwin is also a nerd. Bergwin is more of he's Age of Empires person, but he's programming nerd. Thanks for the stream. Thank you for dropping by. Thank you. Thank you for joining. Thank you for the great questions. Thank you for your company. I'm going to raid Bergwin on Twitch. Good friend of mine. He does a lot of programming stuff, a lot of coding. Let me... The raid message you can write when you get there. Wait, didn't... Oh, I need raid message. And then the winged Nando's arrived. And yeah, this was... Let me hide a question. This was the result of today's stream. I'm going to share this picture later on as well. I love how I'm drawing random scribbles while yapping away. Thanks for the stream. Gotta raid manually from here. Yeah, thank you. Put that up on coffee. Ooh, that could be... I need to show more love to my coffee as well. There's so many things I want to do. I need more time for everything. Why do I like doing stuff so much? I like doing a lot of stuff. If streaming is the only stuff I love doing, I would be... I'm already a great streamer, but I would be even better, but I love doing too much stuff. But yeah, that was it for today. Thanks for dropping by, and I hope to see you in the next one. Bye-bye. Have a great one, y'all.